So welcome everyone to this QU-ATTO webinar. My name is Giorgia Ciuffarella and I'm a PhD student under the supervision of Pascal Salieres at CEA Saclay. Today, it is my pleasure to introduce to you Pascal Salieres. He is the research director at the Atomic Energy Commission at CEA and head of the Attophysics group at LIDIL in CEA Saclay. He has been involved in high harmonic generation since the early days of the field, carrying out his PhD under the supervision of Anne Boulier, and later on collaborating with Maciej Lewenstein and Pierre Agostini here in Saclay. Over the years, he has pioneered a number of phase spectroscopy techniques based on photon or electron interferometry for the characterization and application of harmonic and attosecond pulses. He is participating in the QU-ATTO project and is furthermore coordinating a French national research program on attosecond dynamics and entanglement and decoherence in photoemission. Today, he will introduce us the details of attosecond pulse trains, from their generation to characterization and applications. And with this, I give the floor to Pascal.
Thank you, Georgia, for the introduction, and good morning to all the students of QU-ATTO network. I'm very pleased to present this webinar on this attosecond pulse trains generation, characterization, and application. Okay, so as mentioned by Georgia, I will first start by some reminders about the generation of attosecond pulse trains from a historical and theoretical point of view, and then get in the detail of the attosecond metrology of attosecond pulse trains. And finally, if I have time, I would like to show you how this attosecond metrology has led to new schemes for attosecond spectroscopy, like high harmonic spectroscopy and attosecond photoionization spectroscopy. Okay, so as you know, in 1988, Anne Boulier was the first to observe this high order harmonic generation, and with this characteristic plateau cutoff behavior. And very soon after this observation, the question of the temporal profile of this harmonic emission was raised. And it was proposed in the early 90s that this would correspond to an attosecond pulse train in the time domain, with pulses that are spaced by half the laser period, because you remember that only odd harmonics are produced, which means that you have two laser photon energy band gap between two odd harmonics. And the duration of each peak is inversely proportional to the number of harmonics that you group in your train. And so if you take 13 harmonics, you reach only 100 attosecond duration. Of course, this is only if the n harmonics are in phase. That means have a linear spectral phase. And if they are not, if in particular you have a random spectral phase, then the temporal profile is completely blurred with spikes almost everywhere. So the question is there attosecond synchronization of the higher order harmonics? And to answer this question, there were two problems. The first one is that there was no technique fast enough to measure such short pulses. So people turned to the theory, and from the theoretical point of view, there was no understanding at that time, early 90s, remember, of the emission mechanism. In particular, because we are in this complicated non-perturbative regime. So what people did at that time was a solution of the time-dependent. Okay, do you see this? Okay. The numerical solution of the time-dependent Schrödinger equation. And this was done by Ken Kullander and Ken Scheffer In the States, in Lawrence Livermore National Laboratory, they were very close collaborators, Henriet, and this is what they calculated. This is the phase as a function of harmonic order and the corresponding temporal profile. And as you see, you have a blurred attosecond structure. So that was bad news, because there was no nice attosecond pulse train emerging from this harmonic emission. Slightly later, there was this proposition of a three-step semi-classical model by the same Ken Kullander and Ken Scheffer, and also Paul Corkum independently. And we can, in this case, try to estimate what would be the temporal profile by calculating the classical electron trajectories induced in this laser field. So, for instance, if an electron is emitted at this time in the laser field, it follows, okay, maybe I should use the pointer. Okay, now you can see it. If the electron is emitted at this time in the laser field, it follows this trajectory and return with this kinetic energy corresponding to emission of harmonic 15 in this case. If the electron is launched slightly earlier in the laser field, it follows a different trajectory, comes back with larger energy, and so on, until the point where you reach a maximum, and then you have a decrease of the return energy. So you see that you basically have two families of trajectories that are called the short and the long trajectories that contribute to the same harmonic emission. So if you now select a given spectral range, for instance, from harmonic 15 to 21, you expect that you will have two peaks per half cycle corresponding to the short and the long trajectories. Of course, this is an incomplete model that mixes quantum and classical arguments. So can you believe this? Slightly later, we had the proposal by Maciek Levenstein of a fully quantum model in the strong field approximation that allows the accurate calculation of the temporal profile of the harmonic emission, and this is what he got. So you see, you have indeed many peaks per half cycle, and indeed they correspond to the different electron trajectories contributing to the emission. So that was bad news, because that was confirming what was also observed in the numerical solution of the Schrödinger equation. However, with this model, we could calculate the harmonic dipole and its phase. And what we found is that this phase is very different depending on the laser trajectory. Why? Because actually it is given by the action accumulated along the trajectory. Or if you want, this is the integral of the kinetic energy of the electron along the trajectory. And obviously, this is very different for the short and the long. And this leads to a linear dependence of the phase of the dipole with laser intensity, with a coefficient that depends on the trajectory. And this is great news. Why? Because this plays a major role in the macroscopic emission. You remember in the talk by Henriet in the webinar, she explained that the macroscopic harmonic field that is produced is the coherent sum of all the fields emitted in the medium. And it will be all the most important as all these fields add up coherently. That means are phase matched. And because we focus the laser in the medium, we induce a gradient of laser intensity. And this induces a gradient of the dipole phase that comes into play in the phase matching condition. So this allows you to phase match preferentially the short or the long trajectories in the macroscopic emission. So for instance, if you focus before the jet, then you will select the short trajectories. And indeed, this is what Philippe Antoine could observe in the simulation of the temporal profile of the macroscopic emission this time, with this curve, as you see, where you only have remaining the peaks corresponding to the short trajectories, and it's completely cleaned from all the other trajectories. So you see the macroscopic emission actually cleans up the temporal profile and gives you a very nice attosecond pulse train. Okay, now we are in 96, and there were still no techniques able to characterize this emission. Why is it difficult to perform this attosecond metrology? For invisible femtosecond pulses, there are a number of well-established techniques that are based on nonlinear effects. For instance, second harmonic generation or third harmonic generation in a crystal. Now, these techniques are not applicable to attosecond pulses for two reasons. The first one is that we are in the XUV range with very strong absorption. This means lack of optics and of nonlinear media. Furthermore, attosecond pulses means large spectral bandwidths. Remember that 100 attosecond corresponds to 18 electron volts. So we have to cope with the dispersion over this big spectral bandwidths. And actually, this is only at the end of the 90s that it was realized that a nonlinear process able to handle such broadband XUV pulses was provided by two-photon XUV plus IR ionization of a gas medium. And that was the discovery of Pierre Agostini, who was the first to implement this rabbit techniques that I will present in a second, and allowed the characterization of a train of attosecond pulses, of 250 attosecond pulses. Slightly later, Ferenc Krauss could also perform the first characterization of a single isolated 650 attosecond pulse. And what is quite remarkable is that both techniques, characterization techniques, rely on the ionization of atoms by the XUV beam combined with infrared laser. Giuseppe Sansone did the webinar on this characterization of isolated attosecond pulses, and I will concentrate on the train of attosecond pulses. So what is this rabbit technique? Rabbit is the reconstruction of attosecond beating by interference of two-photon transition. The idea is very simple. We want to access the spectral phase, and as usually, to access a phase, we need interferometry, except that here, instead of using photon interferometry, we will use electron quantum interferometry. And from this spectral phase combined to spectral amplitude, we will reconstruct the temporal profile of the attosecond pulse train. This technique was proposed initially by the group of Alfred Maquet in Paris at LCPMR as early as 96. But it took a few years to implement it in real life. And this was done, as I said, by Pierre Agostini and his collaborator from FOM Amolf in Amsterdam, Harm Müller. So here is the idea. You ionize a gas target, for instance, argon or whatever rare gas atom, because they have high ionization potential, with your harmonic COM. So for instance, if you consider these two harmonics, you produce electron wave packets that actually encode the amplitude and phase of the ionizing harmonic field. This is, of course, provided that the cross-section, the ionization cross-section of the gas is flat. Now, if you add a strong enough infrared field in the 10 to 11 watt per square centimeter with a delay tau, you can dress the continuum in the sense of Claude Cohen analogy, so that you can induce two photon transitions where you can absorb a harmonic photon and an infrared photon, or absorb one harmonic photon and re-emit one infrared photon. And you see that these two processes produce replicas of the initial electron wave packets positioned at the same energy, and that can interfere and encode in their interference the relative phase of the initial harmonics. So let us see in more detail how it works. First, let us look at the two-photon transition amplitude for absorption of the infrared. So the two-photon transition amplitude writes like the product of the harmonic field, amplitude and phase here, by the laser field delayed by tau, and by the two-photon dipole matrix element that is intrinsic to the gas target. The total phase here writes like this, where you have this additional term, which was called initially the atomic phase, because the target was an atom, which is the phase of this matrix element. Now let us turn to the other process where you emit the infrared photon. You have the same for the harmonic Q+2. Now you have the complex conjugate of the laser field, because this is emission of the infrared photon. And you get again this matrix element. The total phase is this. And so finally, when you calculate the intensity of the sideband, you sum coherently these two amplitudes, and you end up with an oscillation term that has three components. The first component is due to the laser phase with respect to the XUV beam. Sorry. And this induces sideband oscillations at 2 omega 0. This is what you observe here when you plot the electron spectrum as a function of the delay between the infrared and the XUV. This is called an electron spectrogram. And what you clearly see, so you see the main bands, the main harmonic bands, and here in between the sidebands. And you see clearly that you have oscillations with a period of 1.3 femtosecond, which is half the laser period. So indeed, we see this sideband oscillation. Now, the phase of the oscillation has two terms. The first term is given by the phase difference of the harmonics that were inducing this ionization process. As I told you, this phase is directly encoded into the electron wave packets and corresponding sidebands. Sorry. Now you have a third term, which is the term coming from the dipole matrix the dipole transition matrix that adds an atomic phase difference. This term usually is very small and can be calculated if you use a well-known gas target. So in the end, you end up with the conclusion the phase of the sideband gives the harmonic group delay. And this is exactly what we were looking for characterizing the attosecond pulse train. Okay, this is the experimental implementation of this scheme, not the initial one that was used by Pierre Agostini at LOA, but the second one that we implemented with Pierre in Saclay. So actually, this is based on a Hole mirror Mach-Zehnder interferometer, where the outer part of the beam is refocused in the gas to produce harmonics and is then blocked by the diaphragm. while the harmonic emission, which is more collimated, passes through the diaphragm and is refocused in the gas jet, the target gas jet. And then we detect the electrons with a time-of-flight spectrometer. Usually we are using a magnetic time-of-flight spectrometer because it has a large collection efficiency. So this gives this photoelectron spectrum for the two harmonics that we were discussing. And then the inner part of the beam, which is much less intense, is also refocused in the gas jet, but does not modify much this emission, passes through the diaphragm, and then is refocused in the gas jet and induces these two photon transitions and appearance of sidebands. And then we can vary the delay between XUV and infrared by using this translation stage, and then observe the varying interferences in the sideband oscillations. Okay, so these are the results, the first result of Pierre Agostini and Harmona. They measured 5 consecutive harmonics, harmonic 11 to 19, so they had 4 sidebands from 12 to 18, and you can see these oscillations at half the laser period. And the striking thing that you observe on this plot is that all sidebands seem to oscillate about in phase. This means that the group delay is constant. And this means that we have close to Fourier transform limited pulses of 250 attoseconds. And you have here the reconstruction. So that was huge news because, of course, this meant that if the harmonic emission is fully synchronized or fully phase locked, then if you were grouping all the big spectra that could be generated at that time it was the harmonic spectrum was extended up to 500 electron volts in some labs. That means more than 300 harmonics. Then a duration of a few attoseconds would be feasible. Of course, that was too good to be true, as we realized just after when we implemented the setup in Saclay to extend the spectral range and look and try to generate shorter pulses. So here is the spectrogram that we measured during the thesis of Yann Meres. It was generation in argon and detection in argon. And now, with more harmonics, you clearly see that the sidebands are not oscillating exactly in phase, but that you have a linear dephasing of the sidebands with increasing order. And indeed, this leads to a linear group delay. Linear group delay means quadratic spectral phase, means attosecond chirp. So the harmonic emission is not fully synchronized, it is chirped. And you can observe this chirp if you reconstruct the temporal profile of a group of harmonics, for instance, here harmonic 15 to 25. And you clearly see that inside each pulse, you have an increase of the frequency of the emission, because this is a positive chirp. Okay, and actually this chirp is very general. You can have it also in neon, where you generate a much higher intensity, and so you can generate much larger harmonic spectra. And actually, we observed a linear group delay over 60 electron volts. Huge bandwidth. So what is the origin of this Atto chirp? Actually, we had it almost under our nose when we calculated the classical trajectories, because you see here that the emission times seems to vary linearly with the harmonic order. Of course, this is this semi-classical model that we were not believing so much in detail, but then calculating using the Levenstein quantum model, we found exactly the same. We found this linear dependence of the emission time in the plateau for the short trajectory, and of course, the opposite chirp for the long trajectories. So this means that the harmonic group delay encodes the emission, or if you want, the recombination time of the corresponding electron trajectories. And this gives us insight into the harmonic generation process. Because now, if we reconstruct the harmonic emission by groups of 5 harmonics, what we observe is actually the fact that the recollisions of the different trajectories occur at different times. So here we have a direct visualization of the ultra-fast electron dynamics in the harmonic generation process. So that was the good news. The bad news is that when we want to produce the shortest pulses, of course, you want to use the largest bandwidths as possible. Now, what you get is this. Because of the Attto chirp, you get strongly distorted emission with all these bounces here and a much larger duration than predicted by the Fourier limit. So actually there is an optimum bandwidth where you still get closer to the Fourier limit while preserving a nice profile. And this leads to 130 attoseconds. Okay, very well. So we have considered up to now only the short trajectories. What happens if you move the focus with respect to the jet? This is what was studied by the group of Dimitris Karambidis in Crete. And they could clearly observe that when moving the jet from after the focus to before the focus, you could clearly see that the Attto chirp was changing sign with many in-between situations. So this means that for getting reliable results with rabbit, you need to select a single trajectory. And this can be done either through phase matching, as I already mentioned, or through spatial filtering, because the long trajectory have a much divergent emission profile. And so using a diaphragm, you can block it significantly. So far, we have considered the plateau region. What about the cutoff region? Because the theory predicts that in the cutoff region, you have fully synchronized high harmonics. And indeed, this is what we measured with Jan Meres. In argon here, you can clearly see that the group delay becomes constant. However, this is not where we will be able to produce the shortest pulses, because the intensity, the harmonic intensity, drops exponentially. So actually, a few harmonics only will be contributing to the attosecond pulse train, and this limits the pulse duration. Okay, so you are left with this Attto chirp. What can you do? First thing you can do is to try to minimize its influence, so to try to improve the synchronization by minimizing the Attto chirp. So how does it scale? The Attto chirp is basically the slope of this curve. So it is given by the extent of the emission times, and this, of course, is proportional to the laser period, and divided by the extent of the harmonic spectrum, which, as you know, is given by the quantum-motive energy. So you are left with a dependence in 1 over the laser intensity and the laser wavelengths. So this is what is given by this slope here. when we try to plot the Atto chirp as a function of laser intensity. And indeed, this is what we measured when doing in xenon, in argon, and in neon, except at high intensities when the medium gets ionized, and then we have strongly perturbed phase relationships. So it is clear from this that the smaller Atto chirp will be obtained in helium, which is the most difficult gas to ionize, and will be obtained with very long driving wavelengths. And indeed, at the moment, this is what has been obtained. Another thing that you can do is to try to compensate for this Atto chirp, to post-compensate for it by propagating in negatively dispersive medium. For instance, using metallic foils. You can see here in the group of Anne a study where they were studying the influence of the thickness of aluminum foil that was that was traversed by the XUV emission. And you see that when increasing from 1 to 3 foils, you could get much better synchronization of the harmonic emission. And this corresponds to narrower or shorter pulse. You can also use gas dispersion, as was performed in the group of Chang-hee Nam in Korea, by increasing the pressure. Here you can see at 40 toes that you have a good synchronization and a short pulse. Finally, you can manufacture XUV multilayer mirrors so that they produce a negative dispersion. And this is what we did in collaboration with Charles Boissin-Boucher at Institut d'Optique, who are the world leaders in producing these XUV multilayer mirrors. And you can see here the results. If we reflect the harmonics on a basic silver mirror, we have this big linear chirp. And if we now reflect the harmonics on a multilayer, on this multilayer mirror, you can get a very good chirp compensation over something like 20 electron volts. And this, of course, produces much shorter attosecond pulses. Okay. Now, what is the state of the art? So this is not completely up to date because here we have the shortest duration for isolated pulses of 50 attoseconds, and we heard already from Giuseppe that 2 recent papers are claiming having produced around 20 attosecond pulses. But in any case, in both cases, we are far from the maximum limit allowed by the harmonic spectrum, because I remind you that it has been possible in the group of Kapteyn and Murnane and also Andreas Baltuska in Austria to generate harmonics or photon energies up to 1.6 kilo-electron volt by driving the harmonic generation process with a 3.9 micrometer laser. And you can see here the spectrum, which has 700 eV bandwidth. And this would correspond to a Fourier limit of 2.5 attosecond. So you see that we are still at least a factor 10 from the Fourier transform limit. So it's still work to do. Okay, what you should now keep in mind is that Rabbit is just an incomplete characterization of the attosecond pulse train, because it gives only an average pulse inside the train, that is probably the one at the maximum of the pulse, the one contributing most of it. And this is clearly shown here for measurements that we did in collaboration with Anne Lhuillier back in 2005 and Katalin Varjou, where we were measuring for different intensities the phase or the group delay of the harmonic emission in neon, and you can clearly see that by slight changes of the harmonic intensity, you change both the timing and, as mentioned already, the Attto chirp. And we have a very good agreement with simulations that are made at fixed peak intensity. So this really shows that you are really dominated by what happens at the maximum of the peak. What does it mean? It means also that you have a variation of the attosecond pulses inside your train, because when you generate at the top of the pulse, you generate this blue at this intensity, this blue pulse, and then later on or early on, you have shifted attosecond pulses and also broader because they are more chirped. So you should keep in mind that you have pulse-to-pulse distortions within the train. Okay. So what can you do to have a better characterization of your train, or better, or most complete characterization? Well, you may try autocorrelation, but actually, and so this was tried in 2003 in the group of Dimitris Karambidis in Crete, using two-photon ionization of helium. So actually, they were using an indium filter to select harmonics that are below harmonic 15, so that you cannot ionize with one photon helium that has a 24.6 EV ionization potential. So you needed two photons to ionize it and produce ions or electrons. And this two-photon ionization signal is actually a second-order autocorrelation or an intensity autocorrelation of the harmonic beam. So they were using a split mirror here to change the delay between the two parts of the beam and measuring then the helium ions that were produced by this two-photon ionization. And this is the result. You see very difficult experiments because obviously you need a very high XUV intensity to induce this two-photon ionization. And they could reach this measurement of 780 attosecond pulses for each pulse in the train. However, note that this is an incomplete temporal characterization because you need to assume a given pulse shape, and this requires a high XUV intensity, as I mentioned. The only technique up to now that has been able to fully characterize the attosecond pulse train is the frog crab technique. So this was already introduced by Giuseppe in his webinar. The idea is that similarly as in the frog, where you use a gate to image or to recover the temporal profile of your field, here in frog crab, this is a phase gate that is provided by the laser field, the dressing laser field that has A as vector potential. Frog crab such in fact means frequency resolved gating for complete reconstruction of attosecond bursts. And this is this animal here. So this is a real crab that is living in Australia, and actually that make jumps like frog. So you use the intense infrared laser pulse as a phase gate to image or to reconstruct the temporal profile of your XUV pulse. I'm not getting in more detail into this because it was already explained. So the first measurement of attosecond pulse train using frog crab was performed in the group of Changhi-Nam in Korea. And you see here the measured spectrogram, full spectrogram, and here is a reconstructed one, and a very good agreement between the two. These measurements, Kyung-Taek Kim, who was the first author in this, said it was the most difficult experiment he did in his life, because you need to combine attosecond stability of the delay over tens of femtoseconds and milli-electron volt spectral resolution over tens of eV. So this is very, very difficult. The nice thing with frog crab is that it applies to attosecond pulses of arbitrary duration and complexity. And this is a simulation that Fabien Quéré did. He was simulating a main pulse of 200 attoseconds with 2 satellites at 1.3 femtoseconds. So in a sense, this is a very short attosecond pulse train with only 3 peaks in the train. And he was gating it, why not, with a chirp laser pulse, so very complicated case. And this is what he could get. This is a frog trace, and here is a retrieved frog. And you see in real time the convergence of the algorithm in recovering both the HUV pulse and the gate, which is actually the vector potential of the dressing laser field. So it really shows the power of this technique. What I find very nice in this case is that it really bridges the gap between rabbit and streaking. You see at low energy, a low kinetic energy of the electrons, you have a trace that really looks like a rabbit trace, because you have interference between the neighboring peaks. While at high kinetic energy, you really have a streaking trace. So this really shows that you should not think in terms of big separation between trains, attosecond pulse trains measured with rabbit, and isolated attosecond pulses measured with streaking. Actually, frog crab is able to reconcile all these techniques in a single very powerful technique. Okay, to be very general, I should also mention another technique called the Attosecond lighthouse that was proposed by Fabien Quéré in Saclay, that maps time to space. So the idea is that here you have you are using for generating a laser a little specific, where the phase front does not correspond to the amplitude front. Okay, and you can get this very easily by misaligning your compressor of the chirpers amplification system. And when you refocus this pulse, what you get is actually a spatial chirp at focus. And this leads to a wavefront rotation. You see the blue frequencies that are on this spatial axis here oscillate, of course, faster than the red frequencies that are on the bottom here. And this leads at the focus to a wavefront rotation, so that the individual attosecond pulses that are produced by each half cycle are actually emitted in different directions. And this is this nice analogy with a lighthouse, where actually you send the light in different direction. And by doing this very quickly, you can actually observe on your spatial detector points that correspond to each individual attosecond pulse in the train. So this is a very nice way of imaging the temporal profile of the attosecond pulse. It was not done in this for this end. Actually, it was more done in the aim to produce isolated pulses from multi-cycle laser pulse, because now you have for each peak here an isolated attosecond pulse that you can then use to do applications. Okay, so now let me conclude these two parts. What we have seen for the generation of attosecond pulse train is that you should not take for granted that you have nice attosecond pulse trains generated when you have a nice harmonic spectrum, because you have two families of trajectories, you have a chirp within each family. But if you do some effort, if you use microscopic selection of a single family and compensate using filters, gas dispersion, Chug mirrors, compensate this chirp, then you will be able to get fully synchronized harmonics, and so very short attosecond pulses. Now, the techniques that we have been discussing are the rabbit, which is an interferometric cross-correlation that gives access to the attosecond structure, but this is just an average pulse in the train. However, it has really opened a whole domain in allowing the detailed investigation of the high harmonic generation process. We have seen the intensity volume autocorrelation that gives partial information on attosecond pulse trains, and finally the frog crab that provides the complete characterization of the attosecond pulse train. Okay, I'm almost done. I don't have much more time to detail the last part. I should add here that I've been discussing only attosecond pulse trains produced from laser matter strong field interaction. Now, as you know, there are attosecond pulse trains that are produced on free electron lasers, on seeded free electron lasers, and you all visited this nice Fermi facility last month or 2 months ago. No, last month. So you know that they are able to produce harmonics of the UV of the 266 laser driving laser, and they have an incredible stability of and control over this attosecond pulse train. This will be detailed in a forthcoming webinar. So that's the reason why I did not discuss this case. Okay, what I would like to just a few minutes to show you is that this attosecond metrology has actually opened new ways of performing attosecond spectroscopy. And we had already a hint of that when we reconstructed the attosecond emission by slices. You remember that we could see how the recollision of the different electron trajectories was encoded into the harmonic emission. So actually the harmonic emission encodes information on the generating medium. And by characterizing the harmonic emission, you can get information on the generating medium. This is the principle of high harmonic spectroscopy, which is, if you want, an extremely nonlinear spectroscopy. And if you use it in molecules, you can get very diverse informations. Why? Because if you consider this recolliding electron wave packet, this is of attosecond duration, so we have seen that already. But an interesting feature is that this is a matter wave. And this matter wave has a de Broglie wavelength that is extremely short. If you consider a kinetic energy of recollision of 35 eV, the de Broglie wavelength is 2 angstrom. So this is on the order of magnitude of the bond length in a small molecule. And remember that the emitted photon that will have even higher energy because you have the IP in addition, so 50 eV, let's say, has a wavelength much longer, 25 nanometer. But this is the electron wave packet that is recolliding and that may encode this information into the harmonic emission. And this is the idea of self-probing. That means the electron wave packet is produced by the molecule to probe the molecule itself. And this gives to probing the molecular structure, but also the molecular dynamics, being vibrational, rotational, or electronic. And this has led to a big field that is right now developing also a lot in solid state, where you can probe phase transition, topological materials, or many different processes in quantum materials very accurately by generating harmonics inside your solid and characterizing this harmonic emission. What I would like just to insist is what was one of the most spectacular demonstration of this technique was in recovering the molecular structure, and more precisely in recovering the molecular orbital. This is the quantum tomography of molecular orbitals that was proposed by the group of Paul Korkum in 2004, where they showed that by measuring the harmonic emission for different angles of the molecules, so the molecules were previously aligned with the first laser pulse, so they were forced to align in a given direction and then probed a different direction by changing the polarization of the generating laser field. And so they could measure the harmonic amplitude. They made an assumption on the phase and then could recover the molecular orbital of nitrogen N2. As you will say, as usually in quantum tomography and also in Fourier transform, usually the phase is the key element. So here they had to assume a pi phase jump at a minimum here. What we did already 6 years later was to measure both harmonic amplitude and phase as a function of the molecular angle. And we could indeed perform this reconstruction of the molecular orbital over this harmonic 17 to 31st in very good agreement with the simulation. So this reconstruction was mainly limited by the accessible spectral range, which was limited here. We would need much higher harmonic orders to get the nice fully resolved molecular orbital. But still, this is access to the wave function here, not its square. So you can clearly see the change of sign of the wave function in between the two nitrogen atoms. And so this was performed in the thesis of Stefan Essler. Okay, so I spoke about high harmonic spectroscopy. Another important consequence of the attosecond metrology is attosecond photoionization spectroscopy. we have seen that we had this information on the target atom here, which was called the atomic phase, that corresponds to the phase of the two-photon transition dipole. Actually, it was shown, in particular by the group of Anne Lhuillier, that this atomic time can be decomposed into the one-photon transition dipole. That means the Wigner time delay. This is the delay of one electron to escape from the molecular potential or atomic potential, plus an additional correction, which is due to the dressing by the laser field. And this continuum delay can be is a universal feature that can be calculated easily. So now you can access this attosecond delay and compare different gases and different ionization from different states in your media. And you can also study resonances, and this leads to the development of the rainbow rabbit, but all this will be developed by David Busto in his webinar. So I will stop here by thanking all my collaborators at Saclay, at LCPMR, at Madrid, with the group of Fernando Martin, at Institut d'Optique, Charles Bourassin, ELM, Frank Lépine, ISMO, and Luca Argenti in Florida. And thank you for your attention.
Thank you, Pascal, for your very nice talk. Indeed, very interesting. So now we can open the floor to if someone has any questions.
Yes. Hello. Thank you very much for this very nice presentation. So you talked about the linear aperture and how to deal with it in the generation chamber. Was the management of the pressure gradient in the cell ever considered to do it?
The gradient, the pressure gradient in the generating cell, you mean? Yeah. I'm not sure. I know that there are a number of simulations that have been performed in order to reduce this gradient or to have the fastest gradient of density at the end of your generating gas cell, so that you are able to couple out the maximum photon energy, the maximum photons out of your medium. I don't know if this was studied in the spirit of decreasing the Atto chirp or playing with the Atto chirp. So if you have good ideas, you can try it. In my knowledge, I don't know any study like this.
Okay, thank you.
I have a question. I don't know if I'm allowed because I'm an old guy. Listen, so most of the things that you were discussing were, of course, based on atomic targets. You went to molecules at the end, but still. My question is, what is the status of generation of attosecond pulse trains in other targets, starting from molecules through simple solids, so I don't know, semiconductors or something like that, to more complicated topological and chiral solids and to strongly correlated systems. So on one hand side of generation of attosecond pulse trains, on the other hand of application of rapid well, for the individual pulses, streaking and this frog and crab frog, which is for both.
Frog crab. This is a crab jumping like a frog, not a frog.
Frog crab, sorry.
Like a crab.
I'm sorry, but I'm not very good in zoology.
Okay. Yeah. Okay. To my knowledge, there have not been any rabbit measurements of frog crab or in for attosecond pulses produced in solid material. They are trying. There have been attempts I know by Ahmed Merji using alkaline atoms, but I'm not sure that it has converged already to any values. The question is that the problem is that when you generate these pulses in a solid state, usually because you are limited in intensity, you are using very long wavelength pulses. So you're producing indeed many. So you're starting from a mid-infrared laser and producing many harmonics, but that do not extend very high in energy. And so if you want to apply the rabbit technique, you need to have a very low ionization potential. Otherwise, you will not see your harmonics. So that's why they propose to use alkaline atoms that have much lower ionization potential. But I'm not sure this has converged.
But maybe does it mean that we need the new technique for solids?
Maybe. As I said, they start from the mid-infrared, so they have a full number of harmonics that are still in the visible and UV range where the usual techniques can be used for characterizing the pulse, the temporal profile of the pulses. But then, as soon as you reach the vacuum ultraviolet, there are no techniques able to measure.
Okay, so can I understand that this is an open problem?
Yeah, I would say.
Okay, thank you. Next project of the grant, then. I had no money, so I had to look.
Thank you, Maciek. Other questions?
Well, if there's another question, I may add one. So you mentioned that we can tweak generation as to select one of the two families of trajectories. Has any work been done on selecting more long trajectories rather than short one? Does this represent a problem experimentally wise?
You mean to select? Is it possible to select the long trajectory? Is it what you?
Yes, but since you mentioned that the long trajectory ones have a higher dispersion angle, and so I guess the Holy Mirror is not fit for this type of trajectory families. How does the experimental work?
Yeah, this is very difficult to work with the long trajectories. The experiment that I showed from the Crete, performed in Crete, was one of the few that was able to really see the influence of the long trajectory, because these trajectories, as I said, they have very long, very big divergence, and so they are much more diffuse. That's one point. The other point is that this harmonic emission from the long trajectory is also more chirped in the sense of the femtosecond chirp. So the spectra of each harmonic are much broader. So you have, let's say, diffusion of the photons both in the spectral and the spatial domain. And this makes the measurements very complicated for this. Now, if you use for the generation, not a Gaussian pulse, but a flat top pulse. Okay? Then the flat top, you don't have any, let's say, you can suppress the intensity gradient either at focus longitudinally, but also temporally and spatially. And by doing this, you would prevent any, let's say, phase modulation of the long trajectory that would, in principle, be overlapped with a short trajectory. So they would not be distinguishable anymore, at least from their from different spatial or temporal properties, but they would still be present in the temporal profile. So that has not been performed yet, I think, although there are projects at CEA to try to implement this idea.
Okay, thank you. Very interesting. So,
yes, I have a question.
Yes.
So when we are working with this kind of very short pulses of, let's say, 20 attoseconds or 40 attoseconds, what are the advantages that a 20 attosecond pulse can offer you over a 40 attosecond pulse? I mean, why do you always want to go to much shorter times if, for me, 40 attoseconds or 30 attoseconds is enough to make a lot of studies?
Mm-hmm. This is the eternal debate of of go west, young man, of going further and further away. Of course, there are so many things that needs to be done that have not yet been done with few 10 attosecond pulses, 50 or even 100. But this is still interesting to push the research also in the direction of the shortest pulse duration and see whether you would be able to reach, for instance, the zeptosecond regime. Because now what you could target are new things. Because now on the zeptosecond domain, where you reach the kilo electron volt energies, now you reach transition in the nucleus, I mean the nuclear transitions.
Exactly.
And then you have a full new physics to be explored of the nucleons inside the nucleus of atoms. So maybe you've heard that this idea of using the thorium to do optical frequency or to transfer the clocks in the VUV spectral domain. So, I mean, there are plenty of things, new things that would be possible if you were able to reach even shorter pulses. But I fully agree with you that there are still plenty of things to be done with the current attosecond pulses. So, and these are not less important. So, definitely continue on your trajectory. No problem. You will do fun things. Other questions?
No, but maybe we should thank you. It was fantastic.
Thank you, Maciek.
yes, Pascal, thank you so much. If we don't have any other question, I suggest we can stop here webinar. And thank you again for the interesting lecture.
Okay. Thanks.
Thank you, Pascal.
Okay.
Bye-bye.
Bye.